So can you now see? Can I try plugging this in again?
Are you still recording the sessions?
Yes. We still recording. Okay, good. Can you see now the screen?
Yes.
Excellent. And that is here is not working. This may not be working, but I can try to switch this over. Okay. All right. Yes, perfect. All right. Okay, perfect. So, should I start? Yeah, okay. Hi, everyone. So I'm ready to give my talk finally. Sorry for the difficulties. So basically, I mean, the short stories we haven't really started on our side either too much. There's a few reasons for that. So one is that officially we weren't really, most of our first months aren't starting yet. The second reason is that our recruiting has been pretty slow, so we don't actually have so much staff allocated yet. Although I guess most of you have met Junkit, who's here but had to leave a bit early. And the third reason is that the actual FZJ superconducting qubit processor has been a bit slow to get started, and the reason for that has been mostly supply chain issues. So you know, the sort of typical stuff that's plaguing a lot of these experimentalist groups in Europe and around the world, and in particular at FZJ, we have a new group that's only been there for about a year and a half. So they're a bit behind schedule, but they're trying to catch up. And so the good news is they finally have all their equipment. They have their fridges, their evaporators, all their sort of expensive equipment in place. And so they should be able to ramp that up, and the plan is to get up to 10 qubits by the end of the year, which would be already enough to sort of validate some very basic usage of the algorithm. But so let me talk at least about what our role is in the project, more or less, as well as some of the challenges that we want to sort of tackle. And so, oh, that's working. Nice. Yeah. So basically, we're mostly involved in these three work packages, which I've sort of reordered from the sort of more low level. So just getting the individual gates to work and being able to simulate those to the level of the quantum circuit, which is already sort of defined by this algorithm, but which we can hopefully further optimize for reasons that, if they're not already obvious, will become clear. And then finally, of course, being able to run these actual algorithms and see how well they work, and to try to further optimize them. And so these are the three work packages that are specifically tied to the experiments. As well as, of course, these other ones, but we're not switching them. And so basically, the idea is that we have this experiment. So there's the experimented force center Mulek, but there are, of course, many other, for example, cloud systems that we can connect to. And so, and then in addition, of course, we also have the ability to do things via simulation, cosmic simulation. And so indeed, there are a lot of choices about, you know, what different methods we can use, what different tools we can use, and you can see that if you talk about this, what's known as a quantum stack of all the different levels of control that we have over this device, that it's, you know, it's extremely complicated, and you know, these are entire subfields of research. But basically, you know, the idea is if everything is running as it should be, then it's a pretty straightforward process. So, you know, you take your quantum algorithm, you put it in some kind of language, which you can then sort of transpile into the native code of the device. Then you have some sort of pulses that are going to implement each of those individual gates on the hardware, and basically those get then sent down to the actual physical device. In practice, there's some problems with that. One is, of course, you have to actually get the device to work, but okay, maybe that's not the biggest problem. The second point is actually that you know, as a function of time, the system will degrade and you have to constantly optimize it. And so, but these are some of the challenges that that we will have to face one way or another, either directly or indirectly. But at least, you know, on the hardware level, we can definitely sort of wash our hands of that. And so, as I mentioned, there's different kind of hardware platforms for that. And we'll just, this is kind of really, but yeah.
Can I just ask on this previous slide, now you have drawn this line.
Yeah.
So where basically you are above that line.
Yes.
And is the interface to the other guys below that line, is that already kind of defined, or is there still work in progress?
It's defined, but it's still work in process. So like everything rudimentary is basically in place, but it's constantly being improved, and let's say a lot of the more advanced functionality is probably not there yet. Yeah, but so I don't know if it's completely visible, but basically there's different kind of software packages that we can use. So actually Pia, who just left, is using Penny Lane. I think most of us are using Qiskit, which is probably good that we kind of all use the same libraries, and there's various reasons that Qiskit is a really good way to go. One is that it's probably the largest ecosystem. And there's a sort of like third-party providers that are also going to be able to provide us with at least rudimentary tools that we can use, so that we don't have to do it ourselves. And if we choose to improve them, and that's also an option, but not necessarily one. And so yeah, so that's sort of the way that at least I would say that we should go. I think everybody here has already made that sort of conclusion as well. And so the third reason is that at Portion Center we actually have our own Qiskit implementation, and that sort of addresses your points as well, Dieter. So basically, this is like the cloud interface for the FZJ devices. There's similarly also code that allows you to sort of to do these pulses, and basically all of this stuff here is essentially in place. At the level of controls, it's also in place, but I mean, it hasn't been very thoroughly tested, so I imagine there's going to be still some more work to be done. But this is what's presently in place. There's no, these are devices you see. These are all places that are not Portion Center. So this is an ETH Zurich chip with 7 qubits. This is a Chalmers 2-qubit chip. I think we also have a Fluxonium one, and then here is an IQM 5-qubit chip that we have cold in our fridge. So the uptime on these devices has been improving, and we can really sort of use these as test grounds. But ultimately, of course, we want to have the much larger Portion Center chips in place, and that's really the purpose of this this QSolid project. So for those of you who don't know, this is the one of the 2 German sort of large projects for building a super microqubit processor, and so the ultimate timeline is that we should hopefully have something, you know, some dozens of qubits by the end of the project to be able to test this.
When is the inauguration?
That's a good question. 2020, end of 26, I think, or early 27.
May I ask something on that as well?
Yes.
So this is the Jülich IBM install machine, the one you are showing, Felix, or is it a different one?
The IQM, yes.
This is IQM, okay.
Yeah.
So a more general question, I mean, I guess we can discuss it later, but are there European level cloud machines for European, you know, universities or member states to access? I guess Tomas is in the call. Maybe if she's not busy doing something else, could answer that. I know that in Greece.
Yes.
Yes.
I can answer that.
Yes.
So, as you might know, there are now what we call the 7 sisters, so 7 hosting sites of quantum machines at supercomputing centers. The first one was on simulator, and it is coming this year, Pascal machine in Jülich, and also in Chancy in Paris, and then there are 6 others. And then the commission is willing to, create a call for more. And so they're actively looking for new vendors. And one of the purposes that they have is indeed to extend it to other countries, including supercomputing centers in widening countries. So if there is interest from Greece, for sure there are possibilities to look into that. Yeah.
Right.
So
Specifically,
yeah.
in my case, I don't want to take Felix time now, but I will be running as well. I mean, my work practice are very similar in the sense that we'll be implementing optimized code for hardware ions and whatever is available, and superconducting as well. I know that we don't have at the level of Greece any access yet, but this is a European project, so that's what I'm asking. Can I go there with the hat of QCFD and say, me or anybody else, all the partners, and say, look, I have this specific circuit, it's a Horizon Real project, can we
I can answer that.
have access?
I can answer that. The answer is yes, because from the flagship project, the one that is run in Munich and the one that is run in Munich/Innsbruck, also with ion traps. Of course, before they renewed their contract, we had letters of support saying that we will get access to their machines and should collaborate with them in a kind of mutually beneficial way, so that we tell them what the kind of needs for the software are, and they tell us what the hardware can do, and so we can actually collaboratively try to kind of merge these two kind of things, requirements and benefits and so on,
right,
hence move forward in the
no, that I already know. I've already contacted Alpine Quantum Technologies,
right, yeah,
Mons, and also the guys at Munich, the Planck QC guys, and
that's different. So
discussing.
plastic is different. That has nothing to do with this.
I mean,
Right.
as far as the FZJ device, I mean, the short story is talk to me, offline at another time. Right now, there's not really any devices to access, but
Right.
will change in the next.
That's what anyway, I don't want to take more of your time. We can discuss this in the comments later. I think it's an important part. Where do we do these things? Yeah. Please go ahead. Sorry for the interruption.
No, thanks for the question. So basically, this Qiskit interface is already in place. And so, but yeah, we're still working on that. And
Sorry, I need to get this right.
and so, yeah, just I mean, I can end soon. I don't have to go too much into my own research, but basically, the idea is, how well will the question is, how well will this algorithm work? I guess that's what everybody wants to know. And so there's various considerations. So if you take some quantum circuit with some circuit width, which is basically the problem size. So how many grid points you can take, for example, and your depth, which basically tells you, how powerful an ansatz can you have. What kind of performance will you expect? And of course, so then there's a single qubit and 2 qubit fidelities, and it's a little bit hard to see here, but basically there's an exponential decay as a function of time. And that comes first and foremost from these fidelities. So every time you apply one of these layers, you basically drop the fidelity. But more generally, we're always going to be limited by the decoherence or the sort of lifetimes of these qubits. So for example, for superconducting qubits, you have lifetimes on the order of, say, 50 to 100 microseconds, and you can expect, in the best case, about 1,000 gates. However, we don't have such high fidelities. Even the IBM devices, okay, they're not the best devices in the world, but those ones have fidelities closer to 99% than 99.9, which means that you're talking about only maybe a few hundred or a couple of hundred gates realistically. And so that's the first consideration. And then the second consideration is that Can you answer, or maybe just click on it? There it is. Okay. So the second consideration is that we have measurements which themselves have their own biases and sources of error, as well as sampling error, as we've already seen with Polstock, for example. And then there's the classical optimizer, which will have its own sort of various issues, such as convergence rates or sort of efficiencies getting stuck in flat parts of the landscape or minimum. And so maybe what I want to say here is that there are different strategies that we can use to try to improve the algorithm. One thing we can do is obviously we can optimize these gates, and that's what I'm an expert in, for example. So I guess I probably won't show it, but I was going to show some slides where we actually took the IBM devices and showed how we could improve the gates on those qubits. So that's one way to make this curve sort of decay less quickly. Something else, obviously, is the actual compilation of these circuits. And so if we can find ways to simplify these or sort of algorithms. So for example, we have a reinforcement learning algorithm that I actually sent around. I actually looked at the draft, but I followed the rules. And so you can optimize this circuit as well. And then there's other things like being able to adapt your gate set specifically to what you want to be able to do. So if you have some of your specific variational gates that you have here, as well as some very specific Hamiltonians that your qubits are going to have, then you can optimize these gates sort of as a function of your Hamiltonian parameters and your angles, and you can thereby sort of make these fidelities higher and these circuits smaller as well. And then the sort of maybe last thing is that one can actually look at doing these things in combination and do sort of hybrid optimization. So for example, being able to do the circuit compilation in conjunction with sort of analog arguments, such as the variational arguments and the actual gate angles are one way, for example, to reduce the sort of the footprint of the circuit and improve things. So yeah, I think that's more or less what I wanted to cover. So we use the tools of optimal control theory, and yeah, and so I'll just quickly step through the slides. These are the IBM gates, what they look like. We can actually improve them. So the idea is to have very simple pulses. These are tested experimentally as well. And then we can use various machine learning approaches to reduce our circuits and to make them more easily learned. There's machine learning ideas to try to find good solutions in the landscape. And this is sort of like an idea for a global optimizer. All of these other global optimizers that we can look at. This most recent paper, we have this hybrid approach where we have this agent which is adding new gates, and this is very similar to what Dieter was talking about with this idea of learning the circuit variationally and trying to minimize as you go along. And here you can sort of think of this extra circuit, the extra elements or layer that you add to your circuit as something that can improve the performance of your circuit, but at the same time you can actually, of course, also change these angles, and so you can actually simultaneously learn the discrete optimization and the continuous optimization for the gradient optimization. Yeah, so I don't think there's any point in going a lot of depth in my research. Basically, we're trying to find ways to optimize this algorithm, but we haven't really started yet. So these are just sort of general tools that we can use in terms of optimizing the gates, optimizing the circuits, and the actual classical optimizer that sits on top of the variational circuit. So, yeah, ready for questions.
Thank you very much. Are there any questions?
I have a few,
Can you say it
but
again?
I guess, yeah, I have a few, especially on the fast forward last part, which is very exciting and interesting and very close to what we do. But I guess maybe on the interest of time and the audience, we can take them offline or later. I mean, I'll ask one at least. If you go
Yeah.
back to the reinforcement learning thing, I guess it's
Yeah.
under. This is related to what the Yale people have been doing, the Vore and so on in preparing quantum state and testing using reinforcement learning. The next slide, the next one. Have been looking where you
This is also
combine,
reinforcement. These are both reinforcement
No.
learning. But,
yeah, where you combine quantum optical control. This one, yeah,
okay.
yeah. So this is using an agent. Okay, yeah.
I can't remember exactly which derivative. I mean,
There are a few works on this reinforcement learning and quantum optical control coming
Yeah, of
out from
course,
the
of
group
course.
these days, where you can use both to prepare optimal quantum states or implement optimal gates. We have been looking at those as well for certain Hamiltonians. We can discuss offline.
Yeah, of course. Yeah, I actually sent the draft for this around, so you can have a look.
This is the latest draft you shared. Okay.
Yes, exactly.
Okay.
Right. So can I just ask you a very quick question?
Yeah.
So at what time can we actually start taking our Qiskit examples and run them on your and what sizes?
Oh, at what size of
Yeah, well, say,
Yeah.
you know, the Qiskit allows you to choose these different backends. And is your backend going to be there at some point? I mean, is this something that one can at some point maybe use for running kind of small examples?
The problem is the gate fidelities are quite bad, but I mean, just as a, just to get the code running,
Right.
I think we can in principle already at least start thinking about that. Like if you, like, I think the first step that we have to do, and this is something we can also discuss, but like, I think there's at least like 3 versions of the codes going around for this, like the Qiskit version of the QCFD code.
Yeah.
And we just need to have a discussion about what the best way to implement that is, and then we can try to port it over to the machines.
Okay, so that would certainly be, even if it's just a
Just
kind of
to prove a
demonstration,
principle, yeah.
that this works, that the pipeline works actually,
Exactly.
even if the results aren't good enough to really do some science with it. I think this would be interesting to just show that it can, in principle.
Yeah.
With 3 or 5. So this is something we can start thinking about now.
Yeah.
Very great, Oscar.
But can I also interject on that? Because of course, what Felix said is totally correct. Of course, for this Open Super Q / Q solid machine, the superconducting qubit machine, but at the same time, we are also installing other machines. We already have a D-Wave machine, which is useless for this. We are also going to have a Pascal quantum simulator, which is pretty much useless for this. But we are also in the process of acquiring another ion trap quantum computer. So this will last a little bit longer. It will take, I guess, a couple of years to be installed, but we can expect that it will be installed during the lifetime of the QCFD project. And so this is so the offering is going to be expanded, and the purpose is exactly to do what we want to do. So I guess a couple of years is the approximate time scale which we can talk about.
If I understand well, Tommaso, then at the moment there is a superconducting machine that in principle we can connect somehow, like at the same way we connect to IBM if we have whatever partnerships.
Yeah, I think this ETH 7 qubit device might be
okay. This is ETH, okay. And there is Pascal, there will be Pascal also. I mean, quantum simulators are actually not that useless. There are some interesting things you can do.
No. Useless for the purpose of this, because here you need a quantum circuit. So for our project, I would say.
Wait for my talk.
Okay, good.
Wonderful. Yeah. I'm also very curious about this.
Yes.
So Tommaso, is what you're saying that this ion trap machine that you're going to install, will that be accessible through Qiskit programs as well?
It will be accessible via Unique. I'm not sure if it will be Qiskit. It may be. This is not yet being specified, actually, because we are in the process of getting the funding. So it is not unlikely that it will be Qiskit, honestly.
Okay. So it might be that then basically it's just another backend that one can choose, and an ion trap will of course expect to have a higher fidelity, gate fidelity there.
Yes.
Okay, great. Okay, thanks. So I guess move on. So yeah, we could of course discuss forever on this, but I think it would be great to move on. I think next is Dimitri, right? So Dimitri, if we can continue talking.
Yes, I need to, yeah, if